Okay, welcome everyone. Today we have Burak Turhan from University of Oulu. He's going to be talking about the software development analytics, some interesting results. Burak is a full professor at the University of Oulu. That's in Oulu, Finland. So uh, himself and his colleague who's going to give another talk that we're going to advertise are visiting from Finland. They're here for a month and they have more weeks left till they finish their work here. So my name is Hakan Erdagmas. Actually, I'm his host. Without too much of the introductions, I'm going to hand it over to Burak.
Thanks, Akam, for the introduction. I guess this is on. Yep. So, thank you for being here. As introduced, I'm Burak Turhan from University of Oulu, Finland, and Oulu is one of the easiest words you will find in the Finnish language. Uh, because this is the department that I'm working in. I have to, I have to focus. I have to focus. Wait a minute. Tietojen käsittely tieteiden laitos. Okay, that means Information Processing Science Department. Okay. So, in case you haven't noticed, Finland is up there and Oulu is even up there. We are close to Arctic Circle, roughly 100 kilometers below the Arctic Circle. So, the temperature, the climate isn't as nice as in California, but we also have some kind of summertime, which we call July only. And for the rest of the year, it's pretty much like this. Uh, but one of the things good about Oulu is we have the longest bicycle roads in Europe, as far as I know. And, we have white nights and long dark nights as well during winter, and this gives us the opportunity to observe great natural events like northern lights or these light pillars. This was actually selected as one of the astronomy photo of the day by NASA, late December 2013. So this is the environment that I'm living, working for the last 5 years, and you see there's nothing much out there to do other than enjoying the natural phenomena. So it gives us great chance to focus on research and all my colleagues in the university. I'm part of the M group in our department, which focuses basically on M software engineering research uh, around requirements engineering, software quality, testing, software analytics, and in recent years more focus on agile and lean software development. And one of the things Finland is very good about is to fund research, public funds. For instance, this company, state-owned company, Digile in Finnish or Digile for you, uh, it's now currently funding a project called Need for Speed, which includes around 40 organizations all across Finland. As far as I remember, 30 of them are industrial partners and about 10 are research partners like universities or research centers. So, within the framework of this project, we also carry on activities for data science and software analytics. And today I will be talking about software analytics part of what we have been doing in that project, and then tie it later on to the core of the talk that we have get the announcement with the cross-project prediction activities. Software analytics. Last last year, yeah, IEEE Software Magazine published a call for paper for software analytics, and interestingly, the special issue name was Software Analytics. So what? I was a bit shocked when I saw the call for paper. What kind of a special issue is that? But then I said, yeah, I've been doing software analytics research for a while, and when I think that I find very good results and present to some practitioners, their first reaction is, yeah, so what? So I think it makes sense. I'm not sure if the yes editors meant that, but it makes sense for me in that sense. What is unique about this is maybe Hakan will tell better, but the special issue has to be distributed between two consecutive issues because there were lots of submissions of high quality, and this could be the first in IEEE software history. So I don't know. So I'm expecting an answer of yes, please. So, like Hakan said, this is the first time in the history of IEEE software, and this shows how software analytics is a hot topic. Okay, so there are many definitions of software analytics. It's kind of a fuzzy, blurry kind of concept. Uh, One of the definitions that I think is from the guest editors of this special issue, and they say, and software analytics is any kind of activity, data analytics activity that will give actionable insights to managers or developers of software by sharing those insights, or that will provide immediate or actionable consequences. And to me and to the community, it also is about sharing multiple things in four steps actually, sharing data, methods, models, and the insights. Some of these activities actually we have been doing for many years and haven't been calling uh, it, referring it by the name of software analytics. For instance, if you're familiar with, or you would be familiar with after this talk, Promise Data Repository. It's out there for more than 10 years, and now it's hosted on Google Code, and it hosts data from software projects, over 100 projects, uh, spanning open source or even some commercial projects developed by certain companies. And a community formed around Promise Data Repository, called the Promise community. By the way, Promise stands for Predictive Models in Software Engineering. And we are also organizing annual conferences. And this year we will have the 10th conference. It's usually co-located with major events in software engineering. For the first half, it was with ICSI all the time. And now for the last 3 years or 4 years, we have been co-located with ESM, Empirical Software Engineering and Measurement Conference. Um, this was sharing data and maybe a little bit sharing methods part. So the Promise community works on developing algorithms or applying smart machine learning applications using software data, trying to predict or come up with insights about software development data. What I see of software analytics is, not sure if everyone will agree, but you have heard terms like empirical software engineering, evidence-based software engineering, and I think data-driven software engineering fits the best for applications of software analytics. And the framework for that, as I see it, is the application of data science. Data science is a set of skills or tools, knowledge that you develop throughout the years with your experience, and then you just go out there, look for data. One unique thing about data science for me is you don't necessarily need to pursue an answer to a question. You just look at the data and try to reveal patterns that are not visible otherwise. And it has been applied to different domains and called business analytics or data analytics. And what I see is if you apply data science to software development data, that's my kind of definition of software analytics within the larger framework of data science. And as I said, you don't necessarily need to have a question to apply software analytics. You can just go out, have a look at the data, and try to identify patterns. So there might be multiple questions that you are, or non-questions you are dealing with, like defect prediction. Today I'm going to talk about that, or process conformance, data-driven continuous improvement, or managing teams. For instance, as an example of data-driven continuous improvement and managing teams, uh, this is an example from the Need for Speed project that I mentioned. Uh, Pilar was also working there, and she was carrying out these surveys with multiple companies. And a part of the survey study was to assess the agility and leanness of the companies. And these findings were related to communication issues between the teams, whether uh, there are any problems or, like the second item says, dependencies, dependency issues between the teams, or the feedback time, particularly focusing on testing. So these findings revealed these issues and saying that between the teams, communication and cooperation is fluent and effective, kind of a average result based on people's uh, insights, opinions. And you know how difficult can be carrying out survey studies, the response rate and uh, other issues involved in carrying difficulties involved in carrying surveys. Then we wanted to go and double check with data triangulation if these insights are supported with what is really going on. And then we generated this beautiful graph that doesn't mean anything. It always requires some explanation for this. So this graph basically is there are two kind of nodes in this graph. You see some text labels, which corresponds to development teams that start with dev, and test teams that start with test label. And there are other kind of nodes that are colorful, and we are not really now concerned about the colors. And what this graph is showing is a visualization of gyro issue repository, the bugs reported in the issue repository. Uh, these colorful nodes correspond to issues, the bugs. And the edges in this graph, the green edges, uh, the red edges correspond to means that this test team has reported this issue and entered it in Java. And the green edges mean the corresponding development team fixed it. So this graph basically shows how different teams communicate, talk over issues. So we just want to have look at this visualization and see some patterns. One pattern is expected pattern or good pattern, like a test team is surrounded by lots of red edges. That is one expect. That's okay. But there were also some unexpected patterns, like the clusters of issues here, which are reported by a development team and then fixed by another development team. So we presented to the managers who are running the projects, and they also agreed that, yeah, this is providing some insights that there are some issues, dependency issues. They are probably working on the same part of the system. And one team introduces a bug and stops working, stops the work of the other team. So this analysis doesn't say much, but it just says by visualization of data that there are some improvement opportunities here just by focusing on the communication issues between those teams. So there are things that might be fixed so that these errors do not propagate between. Yeah. Another example, for instance, process conformance is what we are doing with Hakan, the reason of my uh, visit here. We are looking at the process conformance of developers to test-driven development by this time looking for specific kind of data, installing plugins to developers' IDEs to collect their development activities, and then visualize them, whether they follow the pattern of test-driven development. So in this case, for instance, these two guys from whom we collected data, the pink rectangles say they are test last episodes, development episodes. So this kind of data collection and analysis or analysis of telemetry data, which I would also classify as a software analytics activity. But today, it will be about defect prediction. I know US is not a very soccer or football land, but does anybody remember Paul the octopus? Okay. For those who doesn't know, okay, in the last World Cup, where was it? South Africa. Yeah. Paul was an octopus, I think, in Germany. I'm not sure. So before each game, they put in the environment wherever Paul is living two things with flags of the countries who are playing with each other, and Paul picks one, and he has a great accuracy in predicting who will win the match. He was a phenomenon at the time. Okay. So Paul was an oracle, and in defect prediction, the idea is to find an oracle like that. So to answer this question of where to allocate testing resources or where to test, so the testing activities will start. The development teams. This can be a waterfall fashion or an iterative fashion, like in agile settings. Uh, the testing team or the people who are responsible for testing. Um, Defect prediction provides a decision support system for them to focus on. Okay, there are lots of things here. Where should I test? I have to prioritize my efforts. And defect prediction models are polled for those guys. So maybe more technical sense, it can be seen as a classification problem, a supervised binary classification problem, where the outcome is to predict whether a component, which could be a file or source file, binary file, or could be a component of the system or different levels, a package, uh, whether those entities are fault prone or non-fault prone. That's the idea behind the binary classification for defect prediction. Or it could be modeled as a regression problem to figure out what is the number of expected errors in the next release. So pre-allocation of resources can be used. So this is basically a kind of machine learning problem. It boils down to a machine learning problem if you approach it from that direction. And the predictors in that case become various types of software metrics. I will be discussing about those in a short while. And the dependent variable is whether we have defects or not. So that's the outcome of the oracle. And the problem is basically you cannot test everything in practice. It takes too long. Even if you have kind of server farms that makes regression tests all night through, um, it prevents time to feedback. The testing stage is kind of a bottleneck, and all these kind of claims regarding testing and defects. The later the defects are detected, it costs more. If it propagates through different stages, it costs more. So earlier detection is kind of paramount for achieving quality. And considering from the developer's point of view, the earlier they get feedback about their commits to some uh, code versioning system, um, it will help them much easier, like the unit tests, before they context switch to another task and to fix the problems that they have introduced in the system. And basically, it boils down to, from a management point of view, is software testing is equal to money. It costs a lot, and also no one wants this kind of events to occur during any presentation or in any context, in any uh, business line. So the idea is to get rid of this and not to allow failures to propagate to the field and fix them within a limited time frame. And the idea of defect prediction comes into play here to allocate the limited testing resources by making a prioritization of files. And I will basically keep the unit of analysis to files. It can be anything. It can be method level, file level, class level. So let's say file. It gives a prioritization of the file. And like the poll octopus, it tells the developer or tester team, if you test this one at the top of this list, more likely you will detect some bugs. And in practice, this boils down to the first scenario, you can test everything if you dare to. Even in that case, since the files at the top of the list are more likely to contain defects or bugs, you will detect them earlier and it will give you more time to fix them or rework them. Or scenario two, most likely, you cannot test everything, and once you have confidence in the model, you can just follow the recommendations made by the model, or you can use it to support your expert gut feeling. So, how does it work? It's basically mining software repositories. As I said in the abstract of my call, software development leaves many traces behind, and these reside on different repositories. And it is not limited to what you see in this picture, like the development stage, the source code. You can extract metrics or source code analysis, static code analysis. Then from the configuration management systems, you can see how software is evolving. And from the testing stage, you have access to bug reports. And you can match all of them together to construct a prediction system. And the feedback of the prediction system can be used to guide testing activities, or even it can be used to developers it can be used to guide developers if it's a more real-time kind of a system. Like as soon as they make a commit or as soon as they run a test, it gives them feedback. You should also test those parts. Like this file has a dependency with some other file that you have just changed, so you better make sure you didn't break anything before committing your code. As an example, again, back to the project that we have been doing in Finland, a short case study here. Uh, they have been doing in-house development for wireless communication and automotive industry, and we just picked that big project with the history of one long uh, development data, and uh, we had one point of contact within the company, a guy which I would call a real cool data scientist, and he was able to. We just had break sessions and decided what we should kind of metrics are available to the company. Um, we didn't want to put extra effort to go and collect additional metrics. We just want to start with whatever is available. So he, the data scientist, developed Python scripts and merged all the data that we have collected from different repositories. And basically, the Q repository, the Git version control system, and source code metrics from a static analysis tool. There were some other repositories that is in the process of development, but we were not able to connect to them or consolidate data from them. So we just ignored them and proceeded with whatever is available. For instance, we skipped data from code reviews or inspections, and we skipped data from organizational structure, how different teams communicate with each other, who reports to whom, and we had to skip this automated testing or nightly build reports logs because it was impossible to consolidate those kind of activities. And then from the collected data, it was a commit-based defect predictor. We built a logistic regression model and using the 1 year historical data, and then applied it for the next 2 months, real development data. So for instance, when November came, we just checked the October data, and the prediction model was freezed at the end of September. And it generated this kind of graph, which I will explain now. The x-axis here corresponds to effort measured in terms of the percentage of commits during October. And the y-axis is the percentage of bugs detected, correctly detected by the model. Uh, the red diagonal line here is the baseline, which basically says any prediction model should do better than random. Like if you inspect 50% of the commits, you should be able to detect 90% of the errors. So we should be beating this baseline. And this dashed black line here is showing the best possible scenario if Paul the Octopus was there. He would know everything, though without making any false alarms. And the blue line is the performance of the model. Here, at 20%, you see a special line, the green line. That's just kind of a researcher made up threshold, saying that you have limited resources. Let's say you can only use 20%. You have only time and uh, resources for inspecting 20% of all commits made during a month. If you choose the 20% that the model recommended you to inspect, then with that 20%, you will catch 90% of the bugs as soon as they are committed. Sure.
How did you get this best performance? I mean, you
Because we did,
underwrote
we
MRC?
did this analysis in November, so we knew already which are the real buggy ones in October. And our test set was the October data, all the bugs. Yeah. And we did the same in November, for instance, and this time all the bugs located at the top 12% could be correctly predicted by the model. But the best case was in this case was much closer to optimal. The thing was, okay, I will come back to that. There's another issue with software analytics. These kind of graphs or performance measures usually are creates that kind of so what impression in practitioners. Yeah, we showed them this kind of performance. We were so excited. We can detect bugs 100% in only 10% of the commits. See our graph, and they say, so what? How does it change my life, my day-to-day life? So we try to make different kind of presentations to help them how they can use it. For instance, we come up with cool names, commit hotness ranking. So for each commit, they make an internal company page uh, showing how hot their stuff are, so, and with links to the version control systems or issue tracker that they use in their daily life. So once they commit, they find themselves here. What is the ranking there, or possibility of introducing a bug, or for other managers' view, an overall view of the components directories. What is the risk level of each component? Or more for developers, we were also went to the extreme that we were visualizing the source codes in a web editor and showing the lines which are most likely to include the bugs. But still, we didn't receive that many welcome from the developers. They okay, we can use it for guiding our inspection efforts and maybe for refactoring. And the most useful thing was that silly graph that I showed you in the beginning, the complicated graph. They found it very useful, and it contains no prediction at all. Yeah, with the red edges. Yeah, that was really surprising for us because we were focusing on prediction. Software analytics should be prediction, but it's not the case. So it's about insights, and that graph is giving more insights to the developers or managers. That's like, oh yeah, it's quite back now. I should have provided here this one. They think it might makes much more sense than saying, okay, this file is, they think it's pointing to the obvious. And they say, so I know it already. Yeah, do they really? That's the problem. One follow-up study could be, I think there are a few, like on it. Uh, it's also risky to compare developer insights. Okay, I know these parts are buggy with the outcome of the model and make a comparison between them in a control setting. That might be useful to answer the question today. This was also useful for the teams. Yeah. Yeah. This is just a visualization of whatever in the resides in the issue repository. Yeah, that was our assumption too. And now we want to continue from this thread actually. So you can visualize predictions here, maybe to uh, make them believe it is really something. For instance, give a different color code or different kind of visualization that the model predicts and what were the real bugs, and if it covers more of the buggy nodes, then they might have some confidence. Oh yeah, that might be helpful. These are all options anyway. So back to the future. Okay. So these activities were a summary of the current state of defect prediction, which I label as practical. You have some limited historical in-house repositories from a project history. You have different releases, and then you make predictions for the next release by building some prediction model. And it's limited to whatever local data you have at hand. So this is summary of the current. Again, in kind of a time travel, there's a summary of the past, which resembles very much, actually it's the same thing using software data. Machine learning experiments. Tracy Hall and colleagues from UK made a systematic literature review of all fault prediction studies in software fault prediction, and there are tons of papers about that still coming up, mostly to validate some kind of algorithm, some research group or people generate. Here's a new algorithm I found, so it works, kind of validation studies, but it has no practical impact because they are usually post-mortem. There's a project already finished, completed maybe years ago. You have the fault information and some related software metrics. Okay, you can develop a model and maybe make perfect predictions on that one using the train set test site separation or cross validation kind of approach like we do in machine learning. And at the end, it has no practical impact because that project is over. What I see as a state of future is for training a model, we can use different projects that might be coming within the same company or from different companies. So it's cross project or cross company prediction. So this will enable using data from other projects or other companies as long as they are willing to share their data. So you can use those data to build a predictive model and test it on your new project. And I label it as very practical in terms of practice. However, there are problems because this issue of conclusion instability, which comes from basically from data heterogeneity. The data from different projects might be not really relevant or irrelevant to your context. So there must be ways to find good data for your purposes or for your context and use that data that will make accurate predictions for your case. Or even when you're focusing on some kind of longitudinal study, technology change within your settings, the prediction model that you constructed some years ago needs to be updated continuously because things change. And for that reason, I have been using the concept of dataset shift from machine learning guides into soft prediction models. So I try to interpret it in that terms. So our settings change, our context change, and the models can only predict what they saw earlier, and they should be updated. Or the people who are building those models should be aware that things change and update their models accordingly. Very quickly, going through that is, for instance, one type of dataset shift is covariate shift. Like your covariates in your training set differs from your test set. An example here is just a size-based defect predictor. And this defect predictor is a linear predictor, and it is constructed using these blue or before data here, and with some certain change. Like if you change your business domain, if you change the technologies you use or techniques you use for developing software, and whatever change impacts your the company's traditional operational boundaries, and suddenly the projects you're coming up with has different size characteristics. Then this model is not able to follow up or to or adjust itself to your new settings, and it should be addressed. Or probability shift, prior probability shift, is related to software improvement, process improvement. Is we are always talking about uh, we should improve things, and everybody out there is working to get more quality, better, faster, cheaper, and they make things to achieve that for process improvement with process improvement activities. Or it doesn't need to be at that level. You just have more resources, you more qualification resources, and you have more time to spend on testing uh, your systems. Then you have more quality products, and your defect rates go below without significant changes. Then the models should be updated accordingly. Other types of dataset shift are which I call usual suspects and common in all kind of domains like sample selection bias or imbalance data, which is the case for defect prediction, because the percentage of defects in software datasets are usually, let's say, around 5% to 15%. So the majority of the data is coming from non-fault properties. So it's inherently an imbalanced data problem in prediction. Just to be complete, other types are domain shift and source component shift. Domain shift basically refers to the measurement related issues, uh, like this comment from 2008 that different tools claiming to measure some well-known software metrics, even from source code, they produce different metrics, different measurements. One example could be measuring line of code. I think there are many ways of measuring lines of code. Do you count white spaces? Do you count comments? Or do you standardize the code? So this should be known when you have some data labeled as, okay, this file has 200 lines of code. You should know what lines of code means, how it was measured. And source component shift is the most relevant one in terms of thinking cross context, cross project, or cross company context. Like ISBSG data, ISBSG stands for International Software Benchmarking Standards Group, and they annually collect data from multiple countries, multiple projects. So their data set is really crowded with different type of projects. So inherently, they have this cross prediction issue, but they focus on cost estimation problem, similar one, where the goal is to predict or estimate the cost or effort associated with an upcoming project rather than defect. So this is quick and dirty draft for how to manage dataset shift. There might be missing arrows there, so or maybe irrelevant ones. This is still open work. So some are really trivial, like for addressing imbalanced data, stratification has been used as a standard in machine learning experiments. Or if you have different components in your data, different sources, then you can use mixture models to model different parts, different sources. But today, I want to focus on this relevancy filtering aspect to address this covariate shift, maybe part of the prior probability shift or the sampling issues to answer, do we need all the cross data available out there, or a wiser selection, does it uh, give us better prediction results? So, and hence the following experiments I will explain. So, just to put the options for defect prediction experiments, again comparing, should we go local or global? A company, should they collect their own data or don't care about it and just use data from other projects or companies? The first question is, why do we even bother? Local should be better in all cases. Might be, but there might be also issues related with collecting local data. It simply may not be available or not enough. And it might be too slow to collect that by the time you have enough data to build prediction models, due to that data set shift, uh, your data may not reflect your reality. And the other alternative is to use global or cross context. As I said, there are two contexts which this can be used in: effort estimation, and in there are no clear winners. Barbara Kitchenham used also made a sensitivity review for cross-company cost estimation methods, and I think they identified 8 studies. 4 of them say there is no difference. 2 of them say local is better. 2 of them say cross is better. So it depends. And for defect prediction, our study shows that it can be used as a close gap, just based on, of course, one certain experiment, and which I will explain next. To compare these options, local versus global, first we used the data that you see in this table. There are 10 data sets, and each row corresponds to a data set, and source column shows which source is coming from. The NASA labeled projects come from metric data program of NASA, which was publicly available. I'm not sure if it is still there. So it was mdp.nasa.gov. So, but they are available in Promise Study anyway. And the other source of data was labeled as SoftLab, which we collected from some white good manufacturer back in Turkey. And these projects differ in programming languages, and they are relatively small, I would say, because they're old projects. Here, the number of instances in each project are listed in this column, and this corresponds to not files, but number of methods in this case. And as you see, their defect rates, they are particularly low for qualifying as an imbalanced data problem. So the setting for comparing local versus global was, now I will just forget about the soft lab labeled ones and talk about the NASA projects, since they are different projects, and we treated each NASA project as a different company, assuming that NASA has many subcontractors and but still working or following some rigorous process, and we have no data related with whether these are developed by the same team or different teams. So we are treating them as different projects and companies. So for the 7 NASA data sets, like in a typical machine learning experiment, we just reserved 10% for test sets to validate the model. And we applied 2 treatments. One is treatment CC, corresponding to cross-company. So we train a model on 6 other data sets, and then we test it on the 7th one. And for the treatment within company, We use the remaining 90% of the project data and test it on the one that we reserved here for 10% for testing purposes. And to measure the performance of the models, we make use of we did the classification approach and use this confusion matrix and measure the performance in terms of probability of detection and probability of false alarm. Probability of detection is basically also known as recall, and false alarm is the basically it says C over A plus C is for in reality there are no errors, but our prediction model says there's an error in that component, which is a false alarm. And this is false alarm versus probability of detection. The sweet we want 100% of detection and no false. And here are some initial results from the overall. So this table, the first two rows correspond to probability of detection results, and the last two probability of false alarms, corresponding to cross company labeled with CC or within company labeled with WC. These are the quartiles, performance quartiles, also visualized here. And the visualization works as these bars correspond to medians, and these bars correspond to quartiles. Sorry, these bars correspond to 50%. It marks 50%, and the medians are marked with this black ball. So the pattern here over all 7 NASA projects when the results are pooled is that as you go from within company to cross company predictions, your probability of detection rates increase significantly from a median rate of 75% to 97%. So it increases your capability to detect errors, which is very good news. But it doesn't come for free, because when you look at the false alarm rates, false alarms also go significantly higher when you go from within company to cross company predictions, from a median of 29% to 64%. So you're able to detect more accurately in terms of PD, probability of detection, but you also make too many false alarms. So that was the catch on comparison of these cross company versus within company approach. So it's for all settings. It might applications where you cannot afford to miss any single fault to propagate to the field, then maybe you can afford for this many false alarms. It simply doesn't make sense to switch to cross company. Mhm, 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 mhm. Might be, but rather than hoping, we tried something else to reduce the noise in the data. So we, we developed the simplest thing that we can think of, and this was the thing which occurred to me one night. It woke me up. I couldn't sleep. I just woke up and okay, this might be working, and I just tried to Google if any similar kind of approach exists, and I was happy when I found out there was none. So we used a filtering called, which we call that there are different names, relevancy filtering, and in this case, it's nearest neighbor filtering. And the idea is not to use all available cross data as in raw form, but just to try to pick up the relevant ones. And it's basically an extension of analogy-based learning with a minor difference. So as step one, you just calculate the pairwise distances, simply Euclidean, uh, with your test set to your candidate training set. And for each test instance, you pick the k nearest neighbor from the candidate test set. And using only the unique ones, not allowing any repetitions, you form a pool or a filtered, pruned version of the global test set, which we hope that will filter out the irrelevancies or the noise in the cross data. And now the results for that. For 7 NASA datasets, this time project-wise. Now the same kind of drill. This time each triple corresponds to one dataset labeled as CM1, MW1, or PT1, and the rank of the treatments are the same, only an additional treatment is added called NN. They are either cross-company, nearest neighbor filtered cross-company, or within company. So there are two patterns in based on in the overall data sets. And these two patterns are, for these three, as you go from within company to cross company, we know the pattern, it increases in terms of probability of detection. When you introduce that filtering approach, the nearest neighbor filtering, you lose from your capability of probability of detection, but you're still doing a little bit better than within company or local data. So you not only remove noise, but also it removes maybe some relevant stuff. The second pattern is, for these four data sets, your probability of detection goes even worse than your local capability. The ones marked with blue are all nearest neighborhood. But when we turn the performance measurement from probability of detection to probability of false alarms, so when I change the slides, the order of data sets will not change, and another pattern will emerge. So for those where probability of detection was somewhere in between within company and cross company, probability of false alarms are also somewhere in between. The interesting thing is, for those where probability of detection was worse than the local case, or worse in all three, now has the best false alarm rates. The lowest false alarms, the better. So again, a trade-off here. Yeah, yeah, yes. And now the interesting thing is the external validity of that. I showed you 10 datasets in my datasets slides, and 7 were them from NASA, and 3 of them are from the white goods manufacturer in Turkey. So what we did was, in this setting, we replicated this experiment with the same, but this time we used soft lab data as test sets, and using all 7 NASA data for the pool of cross-company setting, and for treatment of within company, there are 3 projects in soft lab data. We use the 2 for training, and the remaining third one as a test set for checking within company settings. And we also, again, replicated the nearest neighbor filtering here. And the pattern is the same. So this is the within company results. This time it's presented as box plots. So the first one here at the bottom is probability of detection, and the one in between is probability of false alarms. With the within company data, we have pretty much high, around 90% probability of detection, median, and around 30% probability of false alarms, just using the local data available to the company. The second one is a random sampling cross company. So without any kind of nearest neighbor filtering, we see the similar kind of trend. The probability of detection increases, but we observe a ceiling effect here. It was already at 90%, but the bottom line has moved upwards. And the probability of false alarms from 30%, they move to 50% because we introduced alien data to the model. And when you apply the nearest neighbor filtering, again the same trend as in the NASA data, we preserve this time the flow detection rates and false alarms fall to back to 20%, 30% rate. So this basically means the software data in NASA rockets were able to predict bugs in Turkish washing machines. That was the baseline. Uh, this is one of the motivations to for me to pursue this line of research. And after its publication, actually, the uh, number of research activities increased a lot. So the paper that we published it in Empirical Software Engineering in 2009, uh, we are still in 2014, so I should enjoy my last year, is the third most cited article within the last 5 years in Empirical Software Engineering. So there were many follow-up studies trying to beat the NM filtering, and of course it's a stupid one. It's to beat it, but still not beat it. And trying to check the feasibility of cross-component predictions in other settings. For instance, Tom Zimmerman from Microsoft Research, they also use this cross-project learning setting in a larger scale. Uh, they did 622 pairwise comparisons. In our case, it was combining all data and making a prediction for a single project. But in that case, they made pairwise comparisons between projects. And here is a summary of their results. Um, in this one, okay, each node corresponds to a project, and white nodes means this project can predict others. Black nodes mean it's a black hole. It can be predicted by others, but it cannot be used to predict others. And the gray nodes, it works both ways. Pattern, their results is that open source projects, Tomcat, Eclipse, Derby, Firefox, predict defects in other projects, but they cannot be predicted. It's quite weird. And commercial projects like Internet Explorer or Windows kernel or DirectX, they can be predicted. The defects in them can be predicted by open source projects, but they cannot be used for others. But it gives some practical implications. So this means using open source project data, it might be possible to build defect predictors in your context. Yeah, so no, not really. Mm. They recommend domain is important, for instance, in this case. You can use, okay, within this graph, if you extract only the web browser context, so it might be relevant. They are more closer projects. Firefox can predict the bugs of Internet Explorer with 76% precision and 88% recall. That's quite high. But it doesn't work the other way. For me, the question why is still open, and that's why I still keep working on this. Yeah, it's good news. It's good news. Yeah, yeah. My guess is one possible plausible explanation is in open source projects, you have a richer ways of doing things in certain ways. And in commercial projects, you're focused with the processes that you're following, the company culture. Yeah, richer. So This is kind of a meta superset of this one. That's why that part can predict it. But yes, yes, yes. But just speculation. Okay. We went ahead and just tried to identify also some test additional scenarios, two more cases. So when you have data, but it is limited, can you make use of cross-company data? For instance, you just started a new project and you have no prior release data. You're within the first month. You have some limited data collected, and you can build your own prediction model. By adding cross-company data to that, maybe it can improve the prediction. That's case one. And in case two, you already have local project history. You're predicting across releases already, the state of the current. And can you still improve by adding additional data from cross-company? And bottom line was, yes, case one, uh, within company predictions, using only 10% of your available data, plus cross-company data was as good as using 90% of all your data. And for case two, adding cross-company data to your existing one was significantly better than your available local data, but the effect size was quite small. So to summarize, the idea behind this line of research is testing is a costly process, and software leaves trails as you go through the process, and you can make use of the data that you leave in certain repositories, and they can be useful, but its usefulness depends on who is looking at the results. So researchers, practitioners, and you should keep in mind what's the correct way of presenting the results to make them useful for practitioners. So I've been talking about the summary of the past, the machine learning approach of using retrospective analysis of software projects. And then the summary of the current is applying the defect prediction model across releases. And my future vision is to apply it in cross contexts, cross projects or company case. But there are some issues that needs to be resolved, and one possible candidate to solve one of the problems of among others was the relevancy filtering that I introduced, and actually it leads to good results, and these results, washing machine thing and this open source project can predict others, gives the motivation for pursuing further research. And if you're interested, you can follow fromsdata.org and the conferences, or another relevant mining software repositories conference. And you can follow our exit tutorial on data science or software analytics. This was the most attended tutorial last year here in San Francisco, and there will be another edition version of that this year in ICSI in India if you're planning to go there with your colleagues. And late 2014 and early 2015, we have been working on books on these concepts of software analytics, sharing data models, and art and science of analyzing software data. So in case you're interested. So thank you. Yeah.
Yeah, I had a question about the features. What type of features are you? So what I mean by feature, the of course, software source code, which I imagine you're working from,
Mhm.
as opposed to, the binary code or assembly or whatever. So I'm guessing the artifact you're working on is the source code itself.
Yeah.
And I can imagine, there are many different features, and you hinted at them, I think, a little bit, such as, amount of commentary, number of white lines, length of variable names, etc.
Mhm.
Do you have any, what type of features, or how important were the features for your prediction accuracy, for instance?
that differs. So to answer your first question, let me check. Okay, I think I understood. So in these predictions, the results that I showed you, they were based on the nearest neighbor filtering results. They were based only on static code features. McCabe's complexity, Halstead, one the line of code metrics, whatever you can extract from source code itself. But for the company case that I showed you, for instance, there were lots of others, like the ones we can extract from version control repository, like how many people worked on that, the edit frequency of that, if that file has been changed before, were there any reported bugs before, and we are now working on an extended version of that model to incorporate organizational structure on top of that. And as far as I know, there's only one study, again by Microsoft people, Microsoft Research. They they have a set of 8 organizational metrics, which really makes sense, and they show the organizational metrics are the better the metric suite compared to others, like compared to code churn or code complexity. They say organizational metrics are much better, and we just finished a paper about that. And in our context, it wasn't that way, and for instance, pre-release hold history was much better in our case. Yes. Yeah. Yeah. This is the example from the Microsoft research. So they come up with the organizational hierarchy, and they map the source code changes with people in the organizational hierarchy and how many times these engineers, and the lead nodes are the engineers, and they extract metrics from this hierarchy. So like I don't remember now the exact. Let me just make up. So this guy corresponding to which made 60 commits changes is the owner. Is assumed to be the owner of that binary. Here in their case, they work with binary files, not source code files. And this guy belongs to this manager ABCA, and this ABCA has a sub-organization of 7 engineers, and the other engineers may be editing the same parts. Like this guy contributed 30 changes in the same code. But by definition, the owner is E4. So what is the diversity of changes from the same organization? Or if there were another organization here branched, some other engineers might have changed that code. So what is the percentage of, so looking these kind of patterns, metrics they extract from graph, they claim that they show that actually organizations, it's more likely to have, yeah. The theory behind that is, yeah. Yeah.
Another question. I'm not going to take too much time here, but what type of classifiers did you try? Have you tried sort of a broad range of classifiers, or have you found some to be so useful or powerful, that you sort of stick to those? So when I say classifier, I mean things like, naive Bayes,
Yep.
support vector machines, neural networks, your favorites.
My favorite over the years has been my bias for some reasons, I don't know. So the NASA versus SOFLab results were using a naive bias classifier. Uh, but the company cases I showed you, for instance, shows a logistic regression classifier. It was 2000, it should be 9. There's a article in Transactions in Software Engineering by Lessman, and he made an extended analysis of that. He used over 40 classifiers and then assessed them, and he shows the top 15, which are significantly better than the rest, are actually similar to each other, which includes 9 bytes. So after that, actually, the Also, it affected kind of my view of this thing. So it's not really important to focus on specific methods. That it changes, so that the classifier changes from data set to data set. The set of metrics that are relevant usually changes from data set to data set as well. So not specific metrics are useful for all projects, but I would say metric set is what people should focus on. So rather than focusing on, I don't know, number of different people who worked on the code, should be significant indicator. It should be code churn metrics. Should be significant indicators of effects. Category.
For your training, you use project of different categories, right?
Yeah.
What is the impact on the performance, especially on the content?
We haven't checked. For the NASA data, there's actually, I guess, two Java projects and the rest are C and C++. And for the others, they were all the same languages. But yeah, for that case, there are two or three using Java versus C, C++. But we didn't check. Thank you. Thank you.